Hi everyone, thanks for joining us on a new interview on Geo-Insider. Today we'll be talking about some very niche aspects of volcanology, so I really hope you will enjoy that. If so, please like, share and subscribe.
Welcome, Francie, to our Geo-Insider interviews. We are very honored to have you here. Could you please tell us a couple of details about yourself?
Yes, of course. Yeah, I'm also very pleased to be here. Thank you very much for inviting me. Yeah, so I'm Franziska Keller. I'm a fourth year PhD student now at ETH Zürich, where I'm studying caldera cycles and doing a lot of geochemistry work. And yeah, I'm just working already in the field of volcanology for a while now. So having a lot of fun.
Yes, and Francie is a wonderful author for the EGU blog. So you guys should definitely check out her work. It is awesome. I absolutely recommend it. Okay, then let us start. Today's interview is very interesting. We are going to have Francie tell us all about volcanic lightning, what it is, and some of other questions that fall into our theme of natural hazards. So let's dive right into it. Francie, what is volcanic lightning?
Yeah, so volcanic lightning is in theory very similar to the common thunderstorm lightning that everybody knows, right? I mean, in theory, it's just electric discharges that are caused by particle interaction in volcanic plumes instead of thunderstorm clouds. That's basically already it.
Yes, and what kind of particles are actually the ones causing the lightning? Because some sources that I read suggested that it's water molecules, just like the ordinary cause for lightning during storms, and some people suggest that it is actually the ash particles that rub against each other and cause the lightning. So which approach is the correct one?
So I think the way we handled it so far is that ash particles are actually the ones that produce the electrification. So, I mean, if you have a volcanic plume, you have different particles in there, as you already mentioned. So in one big volcanic plume, you have ash particles, which are the majority. Then you have gases, and you also have like water droplets in there. That is true. And sometimes, even if you go to high altitudes, also ice. And so the main mechanisms behind is that you have ash particles and they collide in the plume and they also break apart. And then this actually causes like the charging of those ash particles. And then you have to imagine that those ash particles are transported in the plume, and depending on the size, they get a different charge or they prefer a different certain charge. And then you have those charge pockets that are distributed in the volcanic plume. So at a higher level, you have, for example, more positive charges, at the lower level, more negative charges. And then this creates the lightning. So you have an electric field between those different charges, and then this causes lightning in between.
Yeah, that sounds fascinating. And I also heard that, some people say, well, water also causes this sort of charge redistribution once it turns into ice. So particles start somehow rubbing in a different way. Does that apply here too?
I also read about that already, so that especially ice particles can also interact directly because they are also solid, so they can also contain charges. But to be fair, I am not a specialist in those ice particles because like I was more focused on work that really was on ash particles themselves.
Yeah. So tell us more about your work then. What aspect of volcanic lightning is most interesting to you?
Yeah, so I have to dive back a little bit for that because like it was already like I did my bachelor's and my master thesis both on the interaction of volcanic lightning with volcanic rocks. And especially in my bachelor thesis, it was mostly on volcanic ash. And what we were looking into was basically how does volcanic lightning, which is extremely hot, right? I mean, we can experience temperatures of up to 30,000 Kelvin. So how does that affect the ash particles? Because like those rocks start melting and start interacting, and what does that do to the plume? And so what we did in my work was we wanted to simulate volcanic lightning in the lab. So because like we already like people tried to study the interactions in natural samples, and then they went into the field, they collected ash samples, and what they found were like a couple of small spheres but it were very, very little. So the volume of those spheres was just too small to work on natural samples. So if you really want to make a proper study out of it, you would need to collect tons of samples and search for years probably to have enough of those spheres. And so what we aimed to do was to reproduce those ash particles in the lab. So we developed a setup which was based on an arc welding machine, so the ones that you also use to melt metal and stuff like this. And exactly, so we used this one in a setup in the lab where we created over a very small area a discharge, and then we blew ash particles into this discharge, which has the similar temperatures as lightning actually. So, and that is for us the important aspect. So we wanted to reproduce the temperatures which lightning actually caused. And then we blew the ash particles into this and in this discharge. And yeah, so what we found were actually exactly those little tiny glass spheres of ash particles. Yeah.
Could you tell me more about the geochemical impacts of volcanic lightning?
Yeah, so in my work, we looked on two different aspects. So we looked on the one side on how does this lightning affect the ash particles morphologically. So how does it change from a sharp edged ash particle to what's going to happen afterwards? And this was then basically that we found that they were rounded. So those ash particles got entirely melted. And then when you have a droplet in a plume or falling in the air, you have this melt, and so it gets rounded. So you then have a round sphere. So those are the morphological impacts. And then on the geochemical side, you have to imagine you're melting a proper volcanic glass. And then you put it into temperatures that are extremely high. So those are above the temperatures of a normal magma. And this leads to the volatilization of certain elements. So you have some very volatile elements. And those are, for example, fluorine, chlorine, sulfur, and even sodium and potassium a little bit. And those are the elements that then we also observed are like leaving the droplet. So what we did is, for example, we measured some profiles, some concentration profiles through different ash particles that had an unaffected part and then from lightning affected part. And we saw like when we went through this ash particle from the unaffected part into the affected part, how the concentrations of even those elements then dropped. And that's basically what we saw from that.
Wow, that is crazy. And does this finding somehow change our understanding of the gas composition that comes from a volcanic eruption? Like, how big of an impact does this have?
Yeah. So unfortunately, this was part of my master thesis then, so that we wanted to see if this makes an impact. So what we tried there was to calculate a little bit like how much ash particles do we affect. And the conclusion was that actually we do not affect enough ash particles to change something. So it's also like the concentrations of the gases released from those melted particles are just not enough to change much. So it doesn't change the composition of the plume or affect anything. It's mostly like, yeah, it's interesting, but it doesn't affect it.
Yeah, but what then, in this case, what does make volcanic lightning important?
I think it is here now more on the monitoring side, because you cannot really use volcanic lightning in the sense of that it changes the plume dynamics or the plume composition or something like this. That's unaffected. It's rather on the side of that you can monitor plumes. So especially if you have volcanic eruptions in areas that are not very well, that don't have many people living there, so very remote. And in those areas, you can then, for example, you can trace lightning. Like there are certain networks that can trace lightning discharges all over the world. And then, for example, if you have volcanic lightning in some plumes, you can follow those plumes with those networks and can see where they are, how they move, and even based on the direction of the lightning, you can say in which direction the plume will, for example, travel.
Can you explain that a little bit further?
that is not necessarily my my expertise. So I'm here not really the best person to talk to. I just read a little bit about it. And the way I understood it is that like you have a certain direction of the lightning. So the lightnings apparently go and follow certain azimuths, so angles. And based on those, you can then predict in which direction the plume will go. And that is basically where where volcanic lightning then comes into play for monitoring reasons, and also a little bit in the direction of like how we can predict the direction of plumes and traveling.
Yeah. That is insane. That is crazy. That is so cool. And one last question about plumes. How long does it how long does this plume have the capacity to transfer this electrical charge? Because I would imagine as time goes on, this capacity to build up lightning decreases. So for how long is this on the radar of the instrument that is monitoring it?
I cannot tell that there is a certain time until when it is not there anymore. I mean, it is a bit depending on how dynamic your plume is, but you have a you always have interaction of ash particles there. And it is also proven that volcanic lightning occurs independent of magma composition, independent of plume height. So it's also not necessarily like a small plume produces less than a big plume.
Really?
So exactly. So the plumes are separated in different areas, and based on those different areas, you have different lightning discharges. So you have, for example, at the very low at the vent, you have like a very high outflow of gases, right? So everything is pushing out very fast. So there you have a lot of small lightning discharges, but you can also have the very big ones between the area just above the vent and then the big umbrella at the top of the plume. So it's like a volcanic plume is a very, very, very chaotic environment, I would say. And it's like you have all the time the interaction of ash particles. So I think it is not necessarily timing. It is as long as the plume is there is the potential for volcanic lightning. So.
Okay. Thank you for that answer. I mean, it's obviously a very chaotic environment to study. And my deepest respect for all the people who try and recreate that in a lab, to actually improve the monitoring systems, because coexisting with volcanoes in a modern world is a huge task. It is a challenge, and it definitely necessitates expertise in geosciences. And that's what we're here to underline, that geosciences matter. Okay, Francie, thank you so much. How about well, your journey is fascinating. You went from studying the impacts of volcanic lightning on the morphology and geochemistry of rocks to studying caldera cycles. How did that transition happen?
Yeah, that was actually, I think, a little bit also related to the fact that I realized, okay, volcanic lightning, it is super fascinating, it is super interesting, but it is not a very promising area. So as we already figured out, okay, volcanic lightning can be used to monitor, but that's also about it. And then I was like, okay, let's try out something new. And I'm always fascinated by things that make a big boom, I would say. So volcanic lightning does that, and calderas do that too. So here we have like those gigantic volcanoes that are like have the potential to, I don't know, destroy half of the country around it. So that was also very fascinating for me. So I saw that as a big chance to do something that I also find very fascinating and learn a lot of new things. So I also like it was accompanied with a change of my home country. So I moved from my home country to Switzerland. And so it was just like I saw it as a big opportunity to learn new things. That was mostly it.
Yeah. And do you still see it that way? Do you still feel confident? Do you stand by this decision?
Yes, yeah, I absolutely do. So I think it was a good decision to do that. Also because I see that I learned a lot of different things. I learned, got to know a new university. It's a different environment. It's like I had a great time back in my hometown in the university there, but it's also nice to be somewhere else now. And I got a lot of opportunities here, like doing field work in Japan. I like learned a lot of new methods, techniques, and everything. So that was just great. So that's really a good
Wow.
choice.
I'm very happy for you, honestly. And what is your best highlight so far? What would you say was your favorite moment or the coolest thing you've done?
I think there are a lot of cool things that I was able to do. So it started a bit like with when I was still in my bachelor's and master's, I got the opportunity to go to already a big conference in the US, which is not necessarily like the case if you're still like a master's student. So that was a big highlight for me because it was like the first time that I went to one of those really big conferences and meet new people. And yeah, so this was a great highlight for me. Then I got the opportunity to do an internship at a volcano observatory in Sicily. So I spent 2 months there and was like climbing Etna like every week. And that was also like so beautiful and so great. And now here I got to do my field work in Japan. So it's just like there are so many different highlights that just like make everything so great. I would say.
Oh, that's so sweet. So, yeah, I guess geology is one of those unique fields that offers you the opportunity to meet loads of new people and see loads of beautiful places. So, that's definitely something you should remember if you're considering to study geosciences, in my opinion. Okay, let's move back to our sciencey aspect of the interview. What are calderas, Francie, and what are caldera cycles? I know you have written a wonderful post on that on the EGU GMPD blog, and I will leave a link to that in the description of our interview.
That's great. Yeah, so calderas are, well, okay, calderas is, let's say, the more specific term for it. I think how most people better understand it's supervolcanoes. So calderas basically are really, really big volcanoes that are not built the way we know it. So from every volcano, we like expect this typical positive topography that's just like a perfect triangle. And calderas are the opposite. So calderas have a negative topography. So they basically produce so big eruptions that the magma chamber underneath gets emptied so much that the ground collapses. So you basically have a negative, like a little bowl, I would say, of the volcano. And this is just simply due to the fact that those eruptions are very big. So a lot of material gets erupted, so a lot gets emptied, and then we have this, yeah, falling down of the ground, let's say.
Thank you, Francie. Appreciate it. Okay, here's a challenge for you. Try to explain what a caldera cycle is and its phases in simplest words possible.
Yeah. So as I said, calderas are those very, very, very big volcanoes, right? And they produce really, really big eruptions. So we talk about hundreds of cubic kilometers of material that are erupted. And this needs magma storage underneath. So we have to have really, really big magma chambers under those volcanoes that have magma inside. And this magma changes over the years, right? Because you don't have instantly all the magma there. No, you have to have the magma coming in. This accumulates slowly over time. And that changes. So I think it's like a couple of thousands of 10,000s to hundreds of thousands of years that this magma is there. And so then you have these gigantic eruptions once the volcano is ready. And sometimes you have another one. So sometimes the volcano produces another gigantic eruption. And the caldera cycle then is basically from between those big eruptions. So what happens between those? So in theory, it already starts before, like when we start to accumulate the magma in the crust. But let's say we are now just looking between those very, very, very big eruptions. So we have one at, I don't know, 100,000 years ago and one at 50,000 years ago. And the time in between is what we call a caldera cycle. And this means that you have the big magma reservoir underneath. Then you have sometimes magma coming in, sometimes more, sometimes less, so it changes. Then you have also like a magma is composed of crystals, of melt, of gases, right? And I think the important thing about the caldera cycles is that we have variations in the magma composition. So like the chemistry of the magma changes in the caldera cycle. And what we also can observe is that at a certain point, volatiles, so the gases get an important phase. So at the beginning, for example, we don't have that many volatiles, but then towards the end of the caldera cycle, we assume that we might have like some gases prevailing there. And we can also see differences in small eruptions in between. So we do have those gigantic eruptions, but in between those gigantic eruptions, we also have smaller eruptions of this volcano. So usually if you have a caldera, you have like this big ball of volcano, and in between you have a small stratovolcano, just a normal one. And this one also explodes, right? So this also has the eruption. And this is then where you monitor it basically. So you look like how often does it erupt? Like if it's erupting a lot, then you can say, okay, it is probably just after one of those big eruptions. While if you have very long repose times between those eruptions, it's a sign that like there is something more going on. So the eruptions get bigger and the chemistry changes a little bit. And that is a sign for, okay, something is preparing here. But this is all stuff that we are still working on. So it's still a lot of research that has to be done.
Totally. So I have to give you a 10 out of 10 on that challenge. And I want to ask you, how about, and you partially answered this question already, unrest at the caldera site. How do we know if the caldera is preparing for another big eruption, or it is just, those minor sort of mini eruptions?
Yeah, so that's exactly what I'm working on. So that's still a bit unsure. As I said, there are certain signs like, as I said, the eruption frequency, and yeah, the magma composition is also very important. And so those are the main things that we look at the moment. So we look also at the temperatures and the water content of the magma, because you can, if you have those small eruptions, you can, based on minerals and glass composition, back calculate the temperatures and the water contents that were down in the magma chamber. And there are some things that can help us to like make indications. But we are just trying to get a little bit more of an idea about that. So there is still not too much to say about that.
Yeah, that sounds very complicated. Sounds very complicated. But I wish you best of luck with your work. It sounds meaningful, sounds impactful. I would want to know if a caldera nearby is going to have a massive eruption or not. So I can definitely see how it can impact many, many lives. And I want to thank you for doing that work, and thank you for being with us at our interview again. Okay, how about a very generic question? What is your favorite thing about geosciences? What made you choose to study it?
Wow, that's an important and tough question. I think it's mostly the diversity of the studies, because you have so many different things that you can do. So like I don't really have a routine, let's say, because like you do field work, you do lab work, you do your work on your computer. So it's like so many different things that you can do. And I'm just like, I've been fascinated by volcanoes my whole life, to be fair. So I was like, yeah, let's try that. And so that's just something that I was always fascinated by. So I wanted to do that always. And then I found like earth sciences, and I was like, haha, well, this is a chance to do it. And then just during my studies, I just figured out like that I also really love this change in your daily routine. Like you have the freedom to say, okay, no, today I don't feel like working on my computer, so I will go and do lab work. So it's that, and also like you have the collaboration of so many different topics. So I'm a volcanologist, but I'm always working also with geophysicists. I'm also in contact with people who are doing seismic stuff, so earthquakes. So it's just a lot of collaboration of different areas that always work together, and I think it's also very great. And it's just like in the very, very basics, understanding the planet we are living on, right? So like we have our own home planet and we basically don't have a clue how it's working yet. It's like still so much to discover and to figure out, and it's just something that I really, really like. And it's just like, it is a bit more, you know, yes, we could also study all the planets that are far, far, far away, which is also a part of the Earth sciences, of course, but we can also first of all try to understand the one that we are currently living on, right? And that's just something that I really like about it.
Yeah, you never get bored with geosciences. There's so much for everybody to do, and you can be as interdisciplinary as you like. So there's no limit on that. Okay, Francie, thank you so much for all your wonderful answers. You're an amazing person, and I want to thank you again for tuning into our interview.
Yeah, of course. Thank you very much for having me today.
Thanks for staying with us till the end. We really hope you liked this video. Consider subscribing to the channel and hope to see you on future interviews.